Our universe is a vast, unfathomable expanse, teeming with billions of galaxies, each one a sprawling collection of stars and planets. Yet this is just the beginning. This is the realm we can observe. With the technology at our disposal today, we are able to peer into the farthest corners of space, yet still, there is much beyond the observable limits, tantalizingly out of reach. In this documentary, we embark on an extraordinary journey to explore what lies beyond the observable universe. But first, we must understand the very nature of this observable universe, the scope, size, and limitations of what we can see. The observable universe is defined by the farthest points from which light has had enough time to travel to us since the birth of the universe. This boundary, however, is not fixed. It has expanded and will continue to do so as the universe itself stretches out, ever changing. We begin by exploring this concept of the observable universe, what we can measure and observe with our current technology. It spans approximately 93 billion light years across, a staggering figure that defies human comprehension. This vast expanse encompasses everything we know: galaxies, stars, planets, black holes, and all the other celestial wonders scattered across space. At the heart of it all lies a crucial principle: the speed of light. Light travels at about 299,792,458 meters per second, a universal constant. It serves as our cosmic ruler, measuring distances in space. Yet as light from more distant regions reaches us, the size of the observable universe expands. But there's a catch. Because of the accelerated expansion of the universe, there are regions beyond the observable horizon whose light will never reach us. These vast, unreachable spaces stretch beyond the furthest limits of our vision, and there lies one of the greatest mysteries: what exists in these uncharted territories. Enter dark energy, a force that, while invisible to our senses, exerts a powerful influence over the universe. Responsible for the accelerating expansion of the cosmos, dark energy makes up about 68% of the universe's total energy content. In many ways, it stands as one of the greatest puzzles of modern physics. Alongside dark energy, another enigma persists: dark matter. This invisible, mysterious substance composes roughly 27% of the universe, shaping galaxies and stars in ways that remain elusive. But it's not just the unseen forces that intrigue us. Theories such as string theory and the concept of the multiverse suggest that there could be other dimensions beyond our own, realms that challenge everything we know about space, time, and the very fabric of reality. Could there be parallel universes, each governed by its own laws of physics? Are we truly alone in the cosmos, or is extraterrestrial life thriving just beyond our reach? In this documentary, we dive deeper into these questions, uncovering hidden facets of the universe through groundbreaking discoveries and cutting-edge technologies. We explore the cosmos using a variety of telescopes designed not only to capture visible light, but to detect other forms of electromagnetic radiation, such as radio waves, infrared, and X-rays. This multi-wavelength approach allows us to peer into the universe's dark corners, uncovering hidden mysteries such as the cosmic microwave background radiation, the faint glow left behind from the universe's infancy, providing a glimpse into the very beginning of space and time. As we look deeper, we realize that our universe is mostly empty space, an immense cosmic ocean dotted with galaxies, including our own Milky Way. These galaxies host a stunning array of stars, many of which have planets orbiting them. The sheer number of stars in the observable universe is staggering, more than all the grains of sand on Earth's beaches combined. This fact alone serves as a testament to the boundless scale of our universe. Yet, measuring this immense universe is no simple feat. To understand its vastness, we rely on a variety of methods, each one a testament to the brilliance and ingenuity of human exploration. Central to these efforts is the concept of the light year, the distance that light travels in 1 year, roughly 9.46 trillion kilometers. This cosmic yardstick helps astronomers navigate the unfathomable distances that separate us from distant stars, galaxies, and nebulae. But even with this measure, the observable universe only scratches the surface of what could lie beyond. Our exploration has only just begun. What lies beyond the observable universe? Is there an edge, or does it stretch infinitely in all directions? Could there be other universes entirely different from our own, existing in a space we cannot yet perceive? Join us on this extraordinary journey as we push the boundaries of human knowledge, challenging our understanding of space, time, and the very fabric of reality itself. Together, we will delve into the mysteries of dark matter, dark energy, parallel universes, and the ever-expanding cosmos. The greatest mystery of our time awaits. What lies beyond the observable universe? This journey is just the beginning. One pivotal tool in the astronomer's arsenal is the observation of Type Ia supernovae. These stellar explosions serve as standard candles, allowing scientists to measure distances with remarkable precision. Type Ia supernovae are crucial because their luminosity remains consistent, making them invaluable in estimating the distance of far-off galaxies. By studying how bright these supernovae appear from Earth, astronomers can calculate their distance based on their apparent brightness. However, there's more to the story. When light from these distant objects travels across the expanding universe, it experiences a phenomenon known as redshift. As the light stretches into longer, redder wavelengths, it offers a clue to the rate at which the universe is expanding. This stretching of light allows astronomers to infer the universe's growth, its age, and even its overall size. Further enhancing our cosmic understanding is the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang. This relic radiation provides a snapshot of the universe when it was just 380,000 years old, offering essential clues about its origins. The uniformity of this radiation, coupled with tiny fluctuations, helps scientists determine the geometry of the universe, its expansion rate, and the structure of the cosmos. This primordial light holds the secret to the universe's very beginning, enabling astronomers to calculate the observable universe's extent and even speculate about its potential shape. As our observational tools continue to evolve, technological advancements have played an essential role in expanding our view of the cosmos. Ground-based telescopes and space observatories equipped with advanced sensors and cameras are now capable of capturing light across a vast array of wavelengths, from radio waves to gamma rays. This multispectral observation opens up a whole new dimension to cosmic exploration, revealing hidden phenomena and objects that would otherwise be invisible to our naked eye. In fact, many of the most exciting discoveries in cosmology have come from studying these wavelengths. These observations allow astronomers to look deeper into the universe and uncover far-off objects, such as distant galaxies, stars, and even quasars, which were once beyond our reach. But the real breakthrough in our understanding of the universe stems from the application of Einstein's theories of relativity. Einstein's equations predict how light bends due to gravity, a phenomenon known as gravitational lensing. This bending of light occurs when light from distant galaxies is distorted by the gravitational pull of intervening objects, such as galaxy clusters. By studying these distortions, astronomers can map the mass distribution of the universe and gain a more accurate understanding of the vast distances between cosmic objects. This, in turn, helps refine our measurements of cosmic distances and better understand the structure of the universe. Venturing beyond the observable universe, however, we encounter a realm of cosmic mysteries that remain beyond our reach. These regions where light has not had enough time to travel to us since the universe's birth are a blank canvas for the imagination. Some cosmologists speculate that in these unreachable places, the laws of physics could vary drastically, leading to the possibility of alternative forms of matter, even entirely different versions of reality. Could there be universes that operate under different physical laws, or might the very constants of nature be altered? The idea of a multiverse, a collection of multiple universes, each with its own set of rules, challenges our current understanding of reality. These alternate realms could potentially harbor worlds with life forms, properties, and dimensions we can scarcely imagine. Yet, even closer to home, there are profound enigmas lurking within our own universe. Dark matter and dark energy remain some of the most confounding mysteries in modern cosmology. While we can detect their presence through gravitational effects and the acceleration of the universe's expansion, their true nature remains elusive. These unseen forces might hold the key to unlocking the fundamental workings of the cosmos, altering everything we know about space, time, and the fundamental structure of reality. One of the most tantalizing questions is the very shape and extent of the universe itself. Is it infinite, looping back upon itself in an unimaginable curvature, or does it have a boundary beyond which lies what? Without the technology to peer into these distant reaches, these questions remain speculative, but they are a frontier that ignites the curiosity of humanity. And the quest to answer them fuels our scientific endeavors. Moreover, the possibility of life beyond our observable universe raises both scientific and philosophical questions. If life is possible in the conditions we observe within our cosmos, could it exist elsewhere in regions beyond our reach? What might life look like if governed by different physical laws or constants that deviate from our known reality? This stretches the scope of astrobiology into realms that for now remain within the boundaries of pure conjecture. Yet, it is within these wild speculations that some of the most profound mysteries of existence might one day be revealed. But with profound implications for understanding life's place in the cosmos, the cosmic microwave background radiation, often called the universe's afterglow from the Big Bang, offers more than just a glimpse into the infant universe. It hints at what might lie beyond our observable limits. Tiny fluctuations in this radiation could be markers of processes or objects in the unobservable universe, subtly influencing the realms we can see. These fluctuations could act as breadcrumbs, leading us toward hidden phenomena in the far reaches of existence, far beyond our current grasp. Scientists theorize the potential for physical laws or constants to differ from those we know, creating an entirely new landscape of elements or forces unfamiliar to us. This variance in physical laws could challenge the standard model of particle physics, which, while a remarkable achievement in explaining the particles and forces within our observational reach, acknowledges its limitations. The standard model, after all, only accounts for the observable universe and leaves room for phenomena that remain beyond our comprehension. The existence of such uncharted realms suggests there are laws waiting to be discovered that could radically alter our understanding of the universe's workings. Cosmological models like string theory and the concept of a multiverse provide the frameworks for these unknown elements or forces. String theory in particular proposes the existence of additional dimensions, beyond the familiar 3 spatial dimensions and 1 temporal dimension we experience daily. In these extra dimensions, forces and particles entirely unknown to current science could exist. These forces may have been influencing the universe all along, shaping its very fabric in ways we have yet to understand. The theory opens the door to exciting possibilities, where familiar laws break down and new rules could be written, challenging everything we thought we knew. Moreover, the intriguing possibility of dark matter and dark energy, a mysterious substance that makes up about 95% of the total mass and energy content of the universe but remains largely invisible, raises even more questions. These enigmatic phenomena could be indicative of unknown forces or elements lurking in the shadows of the cosmos, perhaps pointing to gaps in our understanding of gravity and fundamental physics. If dark matter and dark energy are indeed separate from the forces we already know, they could reveal a new branch of physics just beyond our reach. In the uncharted territories of the universe, far beyond our observational capabilities, there may be theoretical particles yet to be discovered. These hypothetical particles, proposed by physicists, aim to explain phenomena that the standard model of particle physics can't fully account for. Their existence could completely rewrite our understanding of the universe and spark a new chapter in the quest for a more complete theory of everything. Among the most fascinating of these theoretical particles are the dark matter candidates, such as WIMPs, weakly interacting massive particles, and axions. WIMPs, massive particles that interact weakly with other matter, are thought to constitute a significant portion of the universe's mass, their presence known only by their gravitational effects on galaxies and clusters. Axions, much lighter and more elusive, could help resolve the strong CP, charge parity problem in quantum chromodynamics, further hinting at dark matter's mysterious nature. Another captivating category involves supersymmetric particles, or sparticles, predicted by supersymmetry, a theory that proposes each particle in the standard model has a corresponding partner with differing spin properties. These hypothetical partners include neutralinos and gravitinos, both considered possible candidates for dark matter. Supersymmetry aims to bridge the gap between the standard model and general relativity, bringing us closer to a grand unified theory of physics, where all fundamental forces and particles are unified into a single framework. Additionally, the theoretical framework of string theory takes things even further, suggesting that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. These strings, each vibrating at a unique frequency, represent different particles, offering a tantalizing view into an entirely new realm of particle physics. The idea that all forces and particles are merely vibrations of these one-dimensional strings opens up a vast number of possibilities, potentially accounting for many particles and forces that exist outside the observable universe. Yet another speculative particle group includes prons, hypothesized subcomponents of quarks and leptons, the fundamental building blocks of matter. If these prons exist, they would point to a deeper layer of subatomic structure, providing new insights into the very composition of matter at a level even more fundamental than we've yet discovered. The search for prons, along with other hypothetical particles, underscores the deeper mysteries of existence that science is only beginning to scratch the surface of. Superstring theory, with its radical reimagining of the universe's fabric, promises to stretch the boundaries of our understanding far beyond the observable cosmos. It challenges our traditional view that the universe is made up of point-like particles and opens up the exciting possibility that the very fabric of reality is composed of strings vibrating in countless ways. By exploring these theoretical frameworks, we inch ever closer to answering some of the most profound questions about the universe, questions that, until now, were beyond our observational reach. Rather than simply existing as particles, the very essence of the universe can be traced back to something far more profound: tiny, vibrating strings. These strings, while imperceptible to our senses, carry the secret to everything we observe in our reality. The vibrational patterns of these strings determine the characteristics of particles, their mass, charge, and behavior, ultimately shaping the entire structure of our universe. Through this lens, space and time themselves are not fixed entities, but dynamic, ever-evolving aspects of our reality. Superstring theory, a groundbreaking concept that pushes the boundaries of physics, introduces a radical idea: our familiar three-dimensional space and one-dimensional time are part of a larger, more intricate framework. The theory proposes additional dimensions that lie hidden from our perception. These extra dimensions are not vast, separate realms, but rather tightly compactified, folded into the very fabric of the universe. These dimensions exist at scales so minuscule, far beyond the reach of our current technological capabilities, making them practically invisible to us. The implications of superstring theory are nothing short of revolutionary. At its core, the theory unifies the universe at its most fundamental level, suggesting that all forces and particles, be it gravity, electromagnetism, or the strong and weak nuclear forces, originate from the same fundamental entity, the string. This profound unity offers a potential bridge between two realms that have long been seen as incompatible: quantum mechanics, which governs the microscopic world of particles, and general relativity, which explains the gravitational dance of stars and galaxies. Superstring theory hints at the possibility of a theory of everything, a single unified framework that could encompass all physical phenomena. Yet the mysteries don't stop here. The extra dimensions proposed by superstring theory open up new possibilities for understanding cosmic phenomena that have eluded scientists for centuries. These hidden dimensions might house forces and particles that interact in ways we can't directly perceive in our three-dimensional reality. This could potentially explain enigmatic concepts like dark matter and dark energy, which continue to challenge conventional physics and our understanding of the cosmos. One of the most intriguing questions that arise from superstring theory and cosmology at large is whether the universe is truly infinite. This question has perplexed scientists, philosophers, and thinkers for generations. If the universe is infinite, it means that space stretches endlessly, containing an unimaginable number of stars, galaxies, and possibly even parallel versions of our own cosmic neighborhood. This concept not only challenges our understanding of the universe, but also forces us to confront deeper questions about existence itself. If the universe is infinite, the observable universe, a mere 93 billion light-years in diameter, becomes a mere speck in the grand scheme of things. This observable universe, defined as the region from which light has had enough time to reach us since the Big Bang, is just a sliver of the potentially boundless cosmos. The implications of an infinite universe are vast and profound. It suggests that cosmic structures and phenomena might repeat endlessly, potentially leading to an infinite number of Earth-like planets, and by extension, the possibility of life forms existing elsewhere in the universe. Infinity also raises significant challenges to our understanding of the distribution of matter and energy. The cosmological principle suggests that on large scales, the universe is homogeneous and isotropic. That is, it looks the same in every direction. In an infinite universe, this principle would imply that large-scale structures like galaxies and galaxy clusters repeat endlessly, extending across the cosmos in an infinite pattern. However, the concept of infinity doesn't easily align with current physical theories. For example, if the universe contained an infinite amount of energy, it would challenge fundamental conservation laws and the principles of thermodynamics that underpin much of physics. Moreover, the idea of infinite versions of Earth, each with minor variations, presents philosophical dilemmas. What does it mean for identity, uniqueness, and reality itself if infinite copies of our planet exist? Is our existence truly special, or is it just one version in an endless sea of possibilities? On a more practical level, the notion of an infinite universe complicates the work of cosmologists. Even if the universe extends infinitely, our observations are forever limited by the speed of light and the age of the universe. The light from distant regions may never reach us, meaning that vast parts of the cosmos will forever remain beyond our reach. This limitation suggests that we may never fully comprehend the universe's ultimate structure, fate, or even its true size. As we peer deeper into space, we are confronted with the realization that much of the universe will always remain a mystery. To better understand the cosmos, we turn to the concept of cosmic inflation. This idea, first proposed by physicist Alan Guth in the 1980s, suggests that the universe underwent an incredibly rapid expansion within the first moments after the Big Bang. This brief yet explosive growth helps explain the uniformity of the cosmic microwave background radiation, an afterglow of the Big Bang that permeates the universe. But what does this rapid expansion mean for the larger picture? If cosmic inflation took place, could there be regions of space far beyond our current observational limits, where the laws of physics play out in ways we've never imagined? As we continue to unravel these cosmic puzzles, superstring theory, the concept of an infinite universe, and the mysteries of cosmic inflation provide us with a new lens through which to view the universe. A universe that is as vast as it is mysterious, as infinite as it is finite, and as complex as our wildest imaginings. But also, Al suggests something truly extraordinary, a universe far beyond what our eyes can see or our instruments can measure. He proposes that there exist phenomena and structures that transcend our conventional understanding of space and time. It's a concept that radically challenges everything we thought we knew about the cosmos. One of the most tantalizing ideas that emerges from inflationary theory is that of quantum fluctuations during inflation. These tiny, almost imperceptible fluctuations in the quantum field could have been stretched to immense cosmic scales, providing the seeds for the creation of the vast structures we see today, like galaxies and clusters of galaxies. Yet, even beyond the observable universe, these fluctuations could have triggered the formation of entirely different regions where physical constants vary, or where entirely different laws of physics govern the universe. This opens up the idea of a cosmic quilt, a patchwork of diverse realms all operating under unique rules, all coexisting in the fabric of space. Another speculative yet captivating possibility that arises from cosmic inflation is the idea of pocket universes. Pockets of space that could contain entirely distinct universes, each harboring its own set of physical laws. These pocket universes, or parallel universes, would exist within a much larger multiverse, with each bubble universe offering a wildly different reality. The very notion that our universe might just be one bubble within a cosmic foam of infinite universes shakes the very foundations of how we perceive reality. Imagine it, each bubble, its own self-contained cosmos, each with its own laws of physics, particles, and even forces that differ radically from our own. It's a concept that truly stretches the boundaries of the mind. The implications of cosmic inflation don't stop there. It is also hypothesized that primordial black holes, the enigmatic objects that don't result from the collapse of stars, but from the intense gravitational forces during the universe's rapid inflationary phase, may be scattered across the regions beyond our sight. These black holes could hold the key to unlocking the mysteries of dark matter, offering crucial insights into the forces that shaped the very early cosmos. Additionally, the immense rapid expansion of the early universe might have triggered the creation of gravitational waves, ripples in the fabric of space-time itself. These waves, caused by the violent stretch of space during inflation, could leave subtle patterns on the cosmic microwave background radiation, an ancient relic of the Big Bang. These faint rippling traces may one day offer a direct glimpse into the first moments of the universe, allowing us to peer into phenomena occurring well beyond the reach of our current observational capacity. The idea of these bubble universes, each a distinct entity in its own right, paints a vivid picture of a cosmos teeming with infinite possibilities. Born from the rapid expansion of the universe following the Big Bang, these universes would be isolated from one another by the ever-expanding space between them. According to the inflationary theory, certain regions of the early universe would have ceased inflating and begun to cool, setting the stage for the creation of individual pocket universes, each with its own evolution. Inside these universes, the conditions could vary drastically. Some may have a reality where gravity, electromagnetism, and the strong and weak nuclear forces are not the same as in our own universe. Such radical differences could lead to entirely new forms of matter and energy, chemistry that we could scarcely imagine, and even completely foreign structures in the cosmic landscape. Meanwhile, others might have galaxies, stars, and other familiar elements, though perhaps in completely different configurations or quantities. In some universes, the physical constants could be just right for the formation of complex life forms. In others, the constants could be so extreme that life as we know it would be utterly impossible. While the technology required to directly detect these bubble universes is far beyond our current capabilities, indirect evidence may one day emerge. Gravitational waves, those ripples in space-time, could hold the key. Anomalies in the cosmic microwave background radiation, the afterglow of the Big Bang, may reveal subtle hints of interactions between our universe and these distant, unseen realms. As we peer into the unknown, we must confront the riddle of dark matter, that mysterious substance that shapes the cosmos yet eludes our direct observation. Dark matter comprises about 27% of the universe's mass and energy, and though it is invisible, its gravitational influence is unmistakable. It serves as the glue that holds galaxies together and forms the cosmic web that stretches far beyond our observable limits. Even in the regions of the universe we cannot see, dark matter is likely still at work, shaping galaxies and clusters, even in the vast expanses beyond our observational reach. These unseen regions might contain entirely new types of galaxies or astronomical objects, entirely distinct from what we know. The relationship between dark matter and dark energy, the elusive force responsible for the universe's accelerated expansion, could hold the answers to the deeper mysteries of the cosmos. How dark matter behaves beyond our observable universe may unlock new understanding, revealing its true nature and the forces that govern it. Current theories propose various candidates for dark matter, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. The search for these elusive particles through both theoretical models and observations is critical to unlocking the secrets of the cosmos. As we venture into the realms beyond what we can see, it's not just dark matter, but the very nature of the universe itself that may prove to be more complex and mysterious than we ever imagined. While dark energy appears uniform within our observable universe, it's entirely possible that variations, or even entirely unknown forms, of dark energy exist in the unobservable regions. These variations could influence the universe's expansion in ways we have yet to fully comprehend, offering new insights into the forces that drive the cosmos. The more we explore, the more we uncover a universe filled with complexities far beyond our grasp. But beyond the observational limits of our current understanding, the very nature of the universe itself could be far more complex and dynamic than we ever imagined. The possibility that the properties of the universe could vary in regions where the expansion accelerates at different rates or where the effects of dark energy are not uniform introduces a level of mystery that beckons further investigation. These variations could open up new realms of inquiry, leading us to reconsider what we know about dark energy. Is it a cosmological constant, an intrinsic value tied to the very vacuum of space, as Einstein once proposed? Or could it be something more fluid, a dynamic field that shifts across space and time? The idea of dark energy evolving over time, like dark matter, but with repulsive rather than attractive gravitational effects, is both intriguing and perplexing. Theoretical models such as quintessence suggest that dark energy might be the result of a field that varies in density across the cosmos. If this hypothesis holds true, we could potentially observe the effects of this field in various ways, perhaps through the cosmic microwave background radiation or in the distribution of galaxy clusters. Such observations would provide us with much-needed clues to the underlying nature of dark energy, hinting at its role in shaping the universe we see today. While direct evidence for the existence of other universes remains elusive, a number of intriguing theoretical frameworks propose methods by which we might infer the presence of a multiverse, a concept that could forever change our understanding of existence itself. One potential indicator of a multiverse might come from studying the cosmic microwave background, CMB, the afterglow of the Big Bang. This nearly uniform radiation field, though largely homogeneous, contains subtle temperature fluctuations. Some theories of cosmic inflation suggest that these fluctuations might be influenced by interactions with other universes. If certain anomalies or unexpected patterns, such as cold spots or unusually large structures, appear within the CMB that cannot be explained by standard cosmological models, they could be the fingerprints of gravitational interactions or even collisions with other bubble universes. This kind of evidence, while still hypothetical, could provide the first glimpse into the existence of parallel universes. Another avenue of investigation into the multiverse theory centers on the constants of nature, such as the gravitational constant or the fine structure constant. These values appear finely tuned to allow life to exist, a phenomenon often discussed in relation to the anthropic principle. In a multiverse scenario, each universe could have different values for these constants, with our own universe's specific values being just one possibility among many. If future research uncovers evidence that these constants vary across different regions of spacetime, it could lend significant weight to the idea that a multiverse exists, where each universe operates under its own set of physical laws. The search for dark flow, which refers to large-scale patterns in galaxy movements that cannot be explained by the visible distribution of mass, offers yet another clue. Some researchers speculate that these unexplained patterns might be the result of gravitational interactions between our universe and others. If verified, dark flow could serve as indirect evidence of the existence of other universes, universes that may exert gravitational influences on ours in ways that we are only beginning to understand. Quantum mechanics also provides an alternative perspective on the multiverse theory, particularly through the many worlds interpretation. This concept posits that every possible quantum event could occur in separate, branching universes. Although the many worlds interpretation is more philosophical than scientific, its implications suggest a reality where the universe constantly splits into multiple versions, each representing different outcomes of quantum events. As our understanding of quantum mechanics deepens, it may open up new ways of thinking about parallel universes, perhaps even offering indirect evidence that these other worlds exist. High-energy physics experiments, such as those conducted at particle accelerators like the Large Hadron Collider, LHC, might also offer valuable insights. The creation of microscopic black holes, or the detection of new particles or forces that do not fit within the standard model of particle physics, could point to interactions with other universes. Such findings could have profound implications for our understanding of the very fabric of reality, suggesting that our universe is but one in a vast multiverse of countless other worlds. The idea that other universes could operate under entirely different laws of physics is both mind-boggling and exhilarating. In such a framework, each universe within the multiverse could be governed by its own unique set of physical constants and laws, leading to cosmic environments that are radically different from our own. This divergence in physical laws could have far-reaching consequences, transforming the nature of matter, energy, space, and time across different universes. One of the most fundamental ways these differences could manifest is in the strength of the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. In our universe, these forces are finely tuned to allow for the existence of atoms, molecules, stars, and galaxies. But in another universe, a stronger gravitational force could lead to the formation of much smaller stars that burn out quickly, or a weaker force might prevent galaxies from forming altogether. Variations in the electromagnetic force could drastically alter the chemistry of such a universe, potentially making life as we know it impossible. Even the masses of elementary particles like electrons and quarks could differ across universes. In a universe where these particles are much heavier or lighter than in our own, the structure of atoms would change, leading to a completely different periodic table. In such a universe, complex chemistry and possibly life might be entirely out of reach. The cosmological constant, which is responsible for the accelerated expansion of our universe, could vary as well. In some universes, a much larger cosmological constant could cause rapid expansion, preventing galaxies from forming. In others, a smaller constant might result in a big crunch, collapsing the universe back on itself, only to begin the cycle again. Alternate universes could also exhibit unique differences in quantum mechanics. Variations in the principles that govern particle behavior could lead to universes where quantum phenomena like uncertainty, superposition, and entanglement manifest in fundamentally different ways. These differences could open up new realms of computation, communication, and energy transfer, potentially leading to technologies and scientific advancements far beyond our current understanding. As we extend our gaze to the far reaches of the cosmos, the possibility of other worlds teeming with life becomes more plausible. While our technology currently limits us to the observable universe, a sphere of space centered around Earth from which light has had time to reach us, there is no reason why other galaxies, planets, and even civilizations could not exist in the unobservable realms beyond. If conditions similar to those on Earth prevail in these distant regions, it is entirely possible that advanced civilizations with technologies far surpassing ours could have already emerged. The concept of the multiverse, where our universe is just one of many, offers a tantalizing glimpse into the infinite possibilities that might exist beyond our understanding. Although the evidence for such a theory remains theoretical, the exploration of these ideas may one day reveal that we are not alone in our universe, but part of a much larger, more mysterious cosmic landscape. But one of many, each with its own physical laws and constants, further expands the potential for advanced civilizations. In some of these universes, the conditions might be even more conducive to the emergence and development of intelligent life than in our own. These civilizations, if they exist, could have explored and understood their universes in ways we can scarcely imagine, potentially even mastering interuniversal communication or travel. The search for extraterrestrial intelligence, SETI, within our observable universe has yet to yield conclusive evidence of advanced civilizations. However, this does not diminish the likelihood of their existence beyond our current observational capabilities. The vast distances and the limitations of our technology present significant challenges to detecting such civilizations. Signals from these distant worlds, whether electromagnetic or other hypothetical forms of communication, would need to traverse immense distances, potentially taking millions or billions of years to reach us, and would require detection capabilities far beyond our current technology. The possibility of advanced civilizations in the unseen cosmos fuels not only scientific inquiry, but also philosophical and ethical considerations about our place in the universe. It prompts us to ponder the nature of such civilizations, their cultures, technologies, philosophies, and how they might have solved challenges that we currently face or will face in the future. The exploration of space, both within and beyond our observable limits, remains one of humanity's most profound endeavors, driven by an innate curiosity and a desire to understand our cosmic neighbors and ultimately ourselves. Imagining the technologies that advanced civilizations beyond our observable universe might possess opens a fascinating window into both speculative science and the limits of our current understanding. These civilizations, if they exist and have developed far beyond our technological capabilities, could employ means of observation and communication that seem like science fiction from our current vantage point. One theoretical technology is the use of advanced telescopes or observation devices far surpassing the power of our current instruments. These devices could potentially manipulate the fabric of space-time itself, allowing them to observe distant galaxies and universes in much higher detail than we can fathom. By bending space-time, these telescopes could bypass the light speed limit that restricts our current observational capabilities, providing real-time images of cosmic events billions of light years away. Another possibility is the use of quantum entanglement for communication. Quantum entanglement is a phenomenon where pairs or groups of particles interact in such a way that the state of each particle cannot be described independently of the state of the others, even when the particles are separated by a large distance. Advanced civilizations might harness this property to transmit information instantaneously across vast distances, breaking free from the constraints of electromagnetic signal travel times. Such a communication network could enable a civilization to remain cohesive over intergalactic or even interuniversal scales. Wormholes. Hypothetical passages through space-time that could create shortcuts for long journeys across the universe represent another frontier that such civilizations might have mastered. If it is possible to create and stabilize wormholes, as some solutions of general relativity suggest, these could be used for instantaneous travel or communication between distant points in space, effectively rendering the vast distances of the cosmos navigable. Additionally, civilizations far more advanced than ours might utilize a form of energy or matter manipulation that is currently beyond our grasp, such as controlling dark energy or harnessing the energy of black holes. These methods could provide the power needed to fuel these incredible technologies, from powering vast, galaxy-spanning telescopes to enabling the construction and maintenance of wormholes or other megastructures for communication and travel. Wormholes, a concept that has fascinated scientists and science fiction enthusiasts alike, are hypothetical passages through space-time that could create shortcuts between distant parts of the universe, or even provide gateways to other universes entirely. According to general relativity, the theory that describes the gravitational interaction of matter and energy, wormholes are possible configurations of space-time that can theoretically connect two separate points in space and time, much like a tunnel with two ends in different locations or times. The intriguing possibility that wormholes could connect us to distant parts of the universe opens up visions of interstellar travel that bypasses the vast distances of empty space, allowing for instantaneous or near instantaneous movement across galaxies. This would not only revolutionize our understanding of travel and communication across the cosmos, but could fundamentally change our place in the universe, potentially unlocking the mysteries of life beyond our world, but also radically transform our understanding of distance and separation. Furthermore, if wormholes truly exist, and some interpretations of quantum mechanics and string theory suggest they could offer a bridge to realms far beyond our own universe. Imagine the possibility. These cosmic tunnels might connect us to alternate realities, a multiverse where different versions of physical laws and constants govern the universe. In such a reality, what we know as the fundamental laws of physics could be entirely different. Through these wormhole connections, we might gain profound insights into the essence of existence, exploring alternate realms that challenge our very conception of reality itself. However, the road to practical application of wormholes is fraught with challenges. Theoretical models predict that to keep a wormhole open, we'd need something known as exotic matter, a form of material with negative energy density. This exotic matter, which doesn't exist in our observable universe, would counteract the natural gravitational forces that tend to collapse a wormhole, keeping it stable enough to traverse. But the creation and maintenance of such a wormhole rely on materials and energy forms that are purely speculative, based on physics far beyond our current understanding. The very act of finding and navigating a wormhole, should it exist, presents monumental challenges. Detecting the entrance of a wormhole, for instance, would require observing its gravitational effects on nearby matter and light, something that demands incredibly sensitive instruments and possibly entirely new ways of observing the cosmos. Space-time, as the very fabric of our universe, is a source of both awe and mystery. Albert Einstein's theory of general relativity laid the groundwork for much of our understanding, yet it is clear that vast swaths of space-time remain shrouded in mystery. While our theories provide a coherent picture of the cosmos, there are undoubtedly aspects of space-time that remain beyond our comprehension, enigmatic forces and phenomena that could rewrite our understanding of reality. One of the greatest mysteries involves dark energy. Though we can observe its influence on the accelerated expansion of the universe, the fundamental nature of dark energy remains a deep unknown. It's possible that dark energy has a role to play in the manipulation of space-time itself, enabling phenomena such as the stretching or contraction of space-time that could determine the ultimate fate of the universe. Another tantalizing frontier for discovery lies at the Planck scale, the smallest, most fundamental level of the universe. At this scale, the very notions of time and space begin to break down. Theoretical physics suggests that space-time itself may possess a quantum structure at this minuscule scale. But how this quantum nature of space-time unfolds into the vast, continuous fabric we observe in the macroscopic world is still one of the universe's deepest puzzles. Unlocking the secrets of this quantum realm could provide the key to uniting general relativity with quantum mechanics, a challenge that has eluded scientists for decades. In the realm of string theory, we also encounter the possibility of additional dimensions, beyond the four we experience. These extra dimensions might harbor unknown forces, particles, or even entire universes that could interact with our own in ways that are impossible to detect with our current instruments. Understanding these higher dimensions and how they might be accessed could open new realms of possibility for scientific exploration. Time itself, often thought to be a simple, linear progression, may also hide deeper mysteries. While we typically perceive time as a constant forward motion, there could be aspects of time that we have yet to discover. Its potential fluidity, its malleability under extreme conditions, or its relationship with space in unusual circumstances, such as near black holes. The possibility of time behaving non-linearly, or of existing in forms that contradict our everyday experiences, could forever change how we understand our place in the universe. In fact, new advancements in theory may soon reveal phenomena that allow for the manipulation of time, creating paradoxes or alternative experiences of temporality that challenge the very notion of reality. Finally, the ultimate fate of the universe, interwoven with the very fabric of space-time, is a profound and still unsolved question. While we have speculative ideas such as the heat death, the Big Crunch, or the Big Rip, these remain educated guesses based on our current understanding of physics. The true end of the universe may involve entirely different mechanisms, influenced by facets of space-time or physical laws that are as yet unrecognized. The nature of cosmic structures, those vast formations beyond the observable universe, also remains largely speculative. Beyond the 93 billion light-year observable universe, there may exist entirely new types of cosmic organizations far larger than anything we have discovered so far. These superclusters, or even hyperclusters, could span hundreds of billions of light years, containing galaxies and clusters on a scale so immense that they might fundamentally alter our ideas of what's possible in the cosmos. These mysteries of space-time, wormholes, and the multiverse represent the frontier of scientific inquiry. They challenge us to reconsider everything we know about the universe, its past, present, and future. But as much as we have discovered, it's clear that we're only scratching the surface. The universe, with its boundless mysteries, promises revelations that could fundamentally alter our perception of reality. But for now, it remains out of reach, awaiting the tools, theories, and insights that will unlock its deepest secrets. But entire webs of superclusters are intricately interwoven in a cosmic web of dark matter and energy, sculpting the universe's large-scale structure in ways we are only beginning to comprehend. The very fabric of the cosmos is shaped by forces and materials that exist beyond the ordinary realms of our understanding. These webs of superclusters are not just random connections, but a deliberate and subtle arrangement, acting like a vast, invisible network threading across the universe. These unseen links bind galaxies, stars, and clusters in ways that are so elusive, so abstract, that they seem almost speculative. However, they remain crucial for understanding the true scope of the universe. Another captivating theory that arises from this cosmic enigma is the idea of dark galaxies, or dark matter conglomerates. These could represent immense accumulations of dark matter with little to no ordinary matter, rendering them nearly invisible to our current detection methods. Conceivably, these entities harbor forms of dark chemistry, or even dark life, operating under principles radically different from anything in our observable universe. Such structures, if they indeed exist, could radically transform our understanding of cosmic evolution and the very distribution of matter and energy across the universe. On an even more speculative frontier, quantum foam structures are theorized to exist at the Planck scale, the smallest conceivable scale in the universe, where classical notions of gravity and space-time break down. But what if these quantum structures extend beyond the microscopic realm and into larger, unobservable cosmic structures? At this level, fluctuations in the fabric of space-time could act as seeds for the creation of galaxies and larger cosmic structures. Current models of cosmic inflation and dark matter do not entirely capture this aspect of the cosmos, but the deeper implications of these quantum foam structures might offer new insights into how the universe itself was seeded and shaped. Another enigmatic feature of the universe lies in the theoretical existence of cosmic strings, defects in space-time that might stretch across the universe in loops or straight lines, potentially forming intricate networks. These strings, predicted by early universe models, could warp space-time in profound ways, influencing galaxy formation and the distribution of matter on an unimaginable scale. These theoretical defects could explain patterns in the universe's structure that current observations cannot fully account for, suggesting that there may be hidden forces at play that shape our cosmic landscape. Then there's the fascinating possibility of parallel universes, an idea suggested by the theory of cosmic inflation. The multiverse concept proposes that our universe is just one among many, each with its own distinct set of physical laws and structures. In this infinite sea of universes, the variety of cosmic structures could be limitless. Some universes might harbor forms of matter, types of energy, and even cosmic architectures so alien to us that they defy description, challenging the very essence of reality as we know it. At the outer edges of what we can observe, the cosmic horizon presents a boundary not of physical space, but of knowledge and perception. This limit is defined by the finite speed of light and the universe's age, preventing us from seeing beyond a certain point. Light from beyond this horizon has simply not had enough time to reach us, leaving vast swaths of the universe forever out of our observational reach. Yet, even at this frontier, theoretical physics offers tantalizing glimpses into what might lie beyond. The redshift of light to extreme degrees, known as cosmological redshift, provides one such clue. As the universe expands, light traveling across it stretches, shifting toward the red end of the spectrum. At the cosmic horizon, this effect is amplified, making light from the edge of the observable universe nearly undetectable. Moreover, this stretching of light implies that objects near the edge of the observable universe appear much older and less evolved, offering a view into the infant universe, a relic from a distant past. Equally captivating is the potential to observe the cosmic microwave background, CMB radiation, the afterglow of the Big Bang, as it would have appeared from distant regions. The CMB serves as a snapshot of the universe when it was only about 380,000 years old, long before stars or galaxies had formed. Observing the CMB from the edge of the observable universe could offer an unprecedented opportunity to study the early universe's properties and the distribution of matter and energy just moments after the Big Bang. Furthermore, current theoretical models predict the existence of vast cosmic structures just beyond our observational horizon, structures such as massive clusters of galaxies, superclusters, and enormous voids. The gravitational effects of these structures might be detectable, subtly influencing the motion and distribution of galaxies near the edge of our observable universe. Additionally, quantum fluctuations from the time of cosmic inflation may leave lasting imprints at this very frontier, offering vital clues about the origins of all cosmic structures. Such insights could not only refine our understanding of inflationary theory, but could also provide a deeper comprehension of the universe's quantum origins. A critical question lies in the uniform temperature of the CMB across the sky, a mystery known as the horizon problem. How could distant regions of the universe, separated by vast distances, have reached such a uniform temperature? The solution may lie in the rapid inflationary expansion of the early universe, a period in which the universe expanded at speeds faster than light, allowing distant regions to equilibrate and explain the CMB's smoothness. Exploring the limits of the observable universe introduces to the speculative realm, where unknown signals from beyond the horizon might contain crucial information about the early universe, cosmic expansion, and perhaps even other universes or dimensions. Among the most intriguing of these signals are gravitational waves. Unlike electromagnetic radiation, which is subject to obstacles and redshift, gravitational waves travel largely unimpeded through the cosmos. These waves could provide an undistorted view of some of the universe's most catastrophic events, such as supermassive black hole collisions or phase transitions in the early universe. Another possible source of signals from beyond the observable universe comes from neutrinos, tiny, almost massless particles that interact weakly with matter. These elusive particles could carry information from the farthest reaches of space, potentially revealing secrets about the formation of the universe's first structures, or hinting at physics that deviates from the standard model. Lastly, the detection of axions, hypothetical particles linked to dark matter, could offer yet another breakthrough. If these particles exist and interact with our universe in ways we cannot yet detect, their electromagnetic signatures could open up entirely new realms of discovery, forever changing our understanding of the cosmos. As we stand on the threshold of the observable universe, the quest for knowledge beckons us to peer beyond the cosmic horizon into the realm of the unknown. What we find there may redefine everything we know about the universe and our place within it, but also offer a window into the larger, unseen cosmos. Black holes, some of the most enigmatic entities we know of, serve as cosmic laboratories for testing the very limits of physics. They lie beyond the observable universe, in regions we cannot yet see or study directly. These distant, mysterious objects tantalize scientists, hinting at the potential to uncover secrets about the universe's most profound mysteries. One of those secrets pertains to quantum gravity. Black holes challenge our understanding by bringing two fundamental forces into conflict: general relativity, which governs gravity at macroscopic scales, and quantum mechanics, which governs the microscopic world. Black holes that exist beyond our observable universe could exhibit behaviors or properties that shed light on this unification problem. Take, for example, the way these black holes evaporate through Hawking radiation. This process might provide essential clues about how gravity operates on quantum scales, potentially offering a pathway toward a unified theory of quantum gravity. Another tantalizing secret lies in the formation and evolution of the early universe. Primordial black holes, hypothetical objects that formed shortly after the Big Bang through the collapse of density fluctuations, could exist in abundance in regions we cannot observe. These objects could help us understand the conditions that existed in the early universe, the distribution of matter, and the nature of dark matter itself. If primordial black holes contribute significantly to dark matter, Detecting their signatures, such as gravitational waves emitted from black hole collisions, could reveal vital information about the universe's dark sector. This would help us better understand the composition and behavior of the unseen matter that makes up most of the cosmos. The information paradox, a puzzle concerning the fate of information that falls into a black hole, also hides profound secrets about the fundamental principles of the universe. Do black holes beyond the observable universe destroy information, as classical theories suggest? Or is the information preserved as quantum mechanics requires? The resolution of this paradox could revolutionize our understanding of information, entropy, and the very fabric of space-time itself. Supermassive black holes located far beyond the observable universe could reveal how galaxies form and evolve on scales and in environments vastly different from those we can currently observe. The interactions between these black holes and their surrounding dark matter halos, interstellar gas, and star systems could provide rare insights into the dynamics of galaxy formation in different cosmic epochs. These black holes could hold clues about processes that shape the universe, presenting an opportunity to witness galactic evolution in ways previously thought impossible. Moreover, the existence of black holes exhibiting properties or behaviors not predicted by current theories could open the door to new physics altogether. This might include black holes in higher dimensional spaces, as predicted by some theoretical models, or black holes with unusual charge or spin characteristics, properties that defy our understanding of astrophysical processes. These anomalies could suggest the existence of exotic particles, fields, or principles of physics that only reveal themselves under the extreme conditions at the event horizons of black holes. While black holes are well-established objects in cosmology, known for their extreme gravitational pull from which not even light can escape, the idea that they might act as bridges or tunnels to distant parts of the universe or even other dimensions remains mostly theoretical. This captivating idea, rooted in theoretical physics, invites us to explore the very limits of our understanding. At the heart of this concept lies the theoretical construct known as a wormhole, solutions to the equations of general relativity that propose hypothetical tunnels through the fabric of space-time. These tunnels could connect two distant points in the universe, or, in some models, link entirely different universes. In this framework, the entrance to a wormhole could resemble a black hole, with a horizon beyond which the laws of physics, as we know them, begin to break down. If wormholes exist, they could potentially allow for instantaneous travel across vast cosmic distances, or even serve as gateways between different universes. However, numerous formidable challenges prevent this from being anything more than a theoretical possibility. For one, the stability of wormholes remains a significant issue. Calculations suggest that they would collapse too quickly for anything to pass through unless they are kept open by exotic matter with negative energy density, that we have yet to discover or fully understand. Furthermore, the very idea of traveling through a black hole to emerge in another part of the cosmos, or even in a different dimension, confronts us with the mystery of singularities. At the core of a black hole lies a point of infinite density, where the laws of physics as we understand them cease to apply. How matter or information could survive this extreme environment and emerge intact remains one of the most profound mysteries in physics. The early universe, a period just after the Big Bang, holds crucial clues about the cosmos that extend beyond the observable limits. This primordial epoch, captured in the cosmic microwave background radiation, provides a snapshot of the universe when it was just 380,000 years old, a moment that offers deep insights into the formation of the universe and the forces that shaped its earliest days. The cosmic microwave background, CMB, is a crucial key to unlocking the mysteries of our universe. By studying the CMB, scientists gain profound insights into the conditions that existed in the early universe, offering tantalizing clues about the vast realms that lie beyond the reach of our current observational capabilities. What the CMB reveals to us is nothing short of remarkable. One of the most striking clues from the early universe is the surprising uniformity of the CMB across the entire sky. This uniformity suggests that different regions of the universe, even those that are not causally connected, meaning that light has not had enough time to travel between them since the Big Bang, share similar temperatures. This observation has provided the groundwork for the inflation theory. The theory proposes that the universe underwent an incredibly rapid expansion just after the Big Bang, smoothing out any initial irregularities. It implies that regions of space that are now separated by vast distances were once in direct contact, and they may share common properties, including the fundamental physical laws that govern them. This hypothesis envisions a universe that is not just vast, but remarkably homogeneous on the largest scales, extending far beyond our observable horizon. At the heart of this rapid expansion lie quantum fluctuations. These tiny variations in density, which were present during the inflationary period, played a pivotal role in shaping the universe's structure. As inflation amplified these fluctuations, they became the seeds for all the future cosmic structures: galaxies, clusters of galaxies, and the sprawling cosmic web. By studying these fluctuations in the CMB, scientists are able to trace the events that unfolded in the universe's earliest moments, providing us with a direct link to the forces that shaped the cosmos. This exploration suggests that similar structures might exist even in the universe that are beyond our observational capabilities. Moreover, the nature and distribution of these fluctuations offer profound insights into cosmic inflation itself. They provide a direct window into the physical processes that took place at the most fundamental level, guiding us to understand the very fabric of the universe. As we delve deeper into the CMB's patterns, we also uncover clues about dark matter and dark energy, two of the most elusive and mysterious components of the cosmos. Dark matter, which we cannot directly observe, exerts its influence through gravity. It shapes the way galaxies and galaxy clusters form and evolve. By studying the slight anisotropies in the CMB, we can infer the presence of dark matter and gain a deeper understanding of its properties. Its effect on the universe is consistent throughout the cosmos, suggesting that dark matter's influence stretches far beyond what we can see. Similarly, dark energy, the mysterious force that is driving the accelerated expansion of the universe, is also woven into the fabric of the cosmos. Its influence extends throughout space-time, affecting the universe's expansion at every scale. What we observe within our cosmic horizon is only a snapshot of its universal dynamics. The study of primordial elements like helium and lithium, which were created in the first few minutes after the Big Bang, further expands our understanding. This process, known as nucleosynthesis, produced the lightest elements in the universe. The relative abundances of these elements are remarkably consistent with predictions and are observed across the cosmos. This consistency supports the notion that the laws of physics and the conditions that govern the universe were uniform from the very beginning, stretching far beyond our observational limits. In addition to these elements, gravitational waves, ripples in the fabric of space-time caused by violent cosmic events, carry a wealth of information about the early universe. These waves could provide unprecedented insights into the very first moments of the universe, potentially revealing phenomena or structures in parts of the cosmos that we cannot currently observe. The detection of these waves from the infant universe might one day unlock the secrets of regions far beyond our current observational reach. At the dawn of the universe, during the first fractions of a second after the Big Bang, the cosmos underwent a phase of rapid expansion known as cosmic inflation. This exponential growth stretched space-time, smoothing out initial irregularities and creating a remarkably homogeneous universe on large scales. This inflationary phase not only set the stage for the universe's large-scale structure, but also laid the foundation for the regions we cannot yet observe. This suggests that the entire universe, even the vast portions beyond our cosmic horizon, shares a common origin and was subjected to the same rapid expansion that shaped it. The quantum fluctuations that occurred during inflation are equally significant. These tiny density variations were magnified by the inflationary expansion and became the building blocks for all cosmic structures, from galaxies to superclusters. The distribution and evolution of matter in the universe's distant regions can be traced back to these early fluctuations. The large-scale structure we observe today is thus rooted in the quantum scale physics that governed the universe's first moments. Furthermore, the synthesis of primordial elements like hydrogen, helium, and traces of lithium occurred minutes after the Big Bang in an event known as Big Bang nucleosynthesis. The relative abundances of these elements, set by the universe's early conditions, are consistent across the cosmos. This consistency not only affects the chemical composition of stars and galaxies, but also serves as an imprint of the universe's initial moments, observable even in the most distant regions of space. The cosmic microwave background is our window into these early epochs. Variations in its temperature and polarization carry vital information about the inflationary epoch, offering insights into the universe's birth and evolution. These variations influence the structure and development of cosmic regions far beyond our reach, reinforcing the idea of a connected cosmos, unified by the same fundamental physical laws. Finally, dark matter and dark energy, two components that together make up nearly 95% of the universe, are deeply tied to the universe's initial conditions. The study of their distribution and behavior in the CMB gives us a unique understanding of how these enigmatic forces shape the cosmos, even in regions we cannot observe. Through the CMB, gravitational waves, and the primordial elements, we are peering into a universe that stretches far beyond what our current tools can detect, opening the door to a deeper understanding of our vast and mysterious cosmos. But these mysterious components govern the universe's expansion and the intricate formation of its vast structures. They impact the development of cosmic regions across every scale and distance, from the most familiar galaxies to the unseen realms at the universe's farthest edges. The known universe, with its myriad forms, from the majestic spiral galaxies to the elegant ellipticals, the elegant lenticulars, and the chaotic irregulars, already presents a vast catalog of galactic structures. Yet, the potential for undiscovered galaxy types, hidden within the universe's most distant or unexplored regions, remains a tantalizing topic for speculation and wonder. One potential category that has captured the imagination of scientists and astronomers alike is the concept of ultramassive galaxies. These hypothetical giants would vastly exceed the size and mass of any galaxy observed so far, potentially dwarfing even the most massive galaxies in our knowledge. Imagine a galaxy containing not just billions or trillions of stars, but potentially spanning hundreds of thousands of light years across, its gravity holding trillions of celestial bodies within an unimaginable expanse. The formation and evolution of such gargantuan galaxies would challenge our understanding of cosmic structure itself, pushing the boundaries of what we thought possible in terms of galaxy formation and size. If such galaxies exist, they could offer groundbreaking insights into the very limits of stellar and galactic creation. Another fascinating yet speculative category of galaxies could be dark galaxies. These galaxies would be composed primarily of dark matter, with very few or even no visible stars. They would be nearly invisible to our current detection methods, which are primarily reliant on the light emitted by stars. However, the very existence of dark galaxies could unlock vital information about dark matter and its role in shaping the cosmos. Given that dark matter is one of the most enigmatic components of the universe, understanding these shadowy galaxies might finally provide the missing pieces to the puzzle, offering a glimpse into the invisible forces that govern the universe's structure and dynamics. Galaxies with highly unconventional forms, resulting from extreme conditions, might also be out there. These could include galaxies that don't fit into our current classification schemes, galaxies whose shapes are highly irregular due to unique or extreme conditions. It is possible that some galaxies have undergone extraordinary evolutionary paths, shaped by powerful gravitational interactions with neighboring galaxies or exposure to intense radiation. Such galaxies might offer a rare opportunity to study the consequences of violent cosmic events and the ways they can transform a galaxy over time. In these cases, the very laws of nature might bend in ways we've never seen before. Equally captivating is the possibility of discovering primordial galaxies, remnants from the very early universe. These galaxies would differ significantly in both composition and structure from those that formed later. Likely smaller and less organized than their modern counterparts, these galaxies would be composed mostly of the first elements, hydrogen and helium, formed shortly after the Big Bang. Their detection would offer a fascinating glimpse into the universe's earliest stages, providing critical data on the conditions that prevailed in the aftermath of the Big Bang and the birth of the cosmos itself. The discovery of such galaxies would be a monumental leap in our understanding of the universe's origins, shedding light on the very first stars and the processes that led to the universe as we know it. Even more speculative are the possibilities suggested by the theory of mirror galaxies. If a parallel universe exists, governed by its own set of physical laws, mirror galaxies could form a part of that universe. These galaxies would be composed of mirror matter, interacting with our known universe in fundamentally different ways. Though entirely hypothetical, these galaxies could potentially be detectable through indirect gravitational effects or other unusual cosmic phenomena. The mere suggestion of mirror galaxies opens up an exciting, if speculative, avenue for future exploration, one that could expand our understanding of the universe to dimensions beyond the observable realm. As we venture beyond the cosmic horizon, scientists and engineers continue to push the limits of technology, developing new instruments and methods designed to peer deeper into the cosmos than ever before. These advancements not only promise to improve our view of the distant universe, but could also help reveal regions beyond the observable universe, areas of space we've never before been able to observe or even imagine. At the forefront of these technological advancements are the next-generation telescopes, both ground-based and space-based, that are set to revolutionize our observational capabilities. Ground-based observatories such as the Extremely Large Telescope, ELT, being constructed in Chile, and the 30-meter telescope, TMT, planned for Hawaii, will feature mirror diameters of 30 to 40 meters, significantly larger than any current telescopes. These giant instruments will be able to collect more light from faint, distant objects, allowing astronomers to study the earliest galaxies and stars in unprecedented detail. Meanwhile, the James Webb Space Telescope, JWST, launched in December 2021, represents the pinnacle of space-based observatories. With its massive mirror and advanced instruments designed to observe the universe in infrared light, JWST will be able to peer through cosmic dust clouds, unveiling galaxies formed shortly after the Big Bang, and pushing the boundaries of what we can observe. In addition, radio astronomy is undergoing a revolutionary leap with projects like the Square Kilometer Array, SKA, an international effort to build the world's largest radio telescope. The SKA will utilize thousands of dishes and up to 1 million low-frequency antennas scattered across vast distances. This will allow astronomers to detect faint radio waves from the cosmic dawn, an era when the first stars and galaxies began to form, offering crucial insights into the early universe's structure. Similarly, gravitational wave observatories such as LIGO and Virgo have already opened a new window onto the cosmos, detecting ripples in space-time caused by the collision of black holes and neutron stars. Upcoming projects like the Laser Interferometer Space Antenna, LISA, aim to detect gravitational waves from a broader range of sources, potentially including primordial waves from the universe's first moments, providing evidence for cosmic inflation and offering insights into the universe's earliest stages. Additionally, the development of neutrino observatories, such as the IceCube Neutrino Observatory at the South Pole, represents a promising frontier. These observatories are designed to detect high-energy neutrinos, nearly massless particles that can pass through dense regions of space without interacting with matter. Neutrinos carry valuable information about distant cosmic events and structures, providing a unique perspective on the universe that electromagnetic radiation cannot. Finally, advancements in computational astrophysics, alongside the development of sophisticated algorithms and simulations, play a vital role in pushing the boundaries of our understanding. By combining observational data with theoretical models, scientists can simulate the evolution of the universe, from the Big Bang to the present day. These simulations help to explore structures and scenarios that lie beyond our direct observational capabilities, filling in the gaps of our cosmic knowledge and allowing us to visualize the universe's unfolding on scales we can't directly observe. But what if the key to unlocking the deepest secrets of the universe lies not in our traditional understanding of physics, but in the mind-bending world of quantum mechanics? Quantum computing, an emerging technology based on the very principles that govern the subatomic world, could fundamentally reshape the way we explore the cosmos. At its core, quantum computing harnesses the strange, unpredictable behavior of particles to perform calculations that were once thought to be impossible. Imagine, for a moment, the ability to simulate the most enigmatic cosmic phenomena, from the birth of stars to the origins of the universe itself. Quantum computers, operating on principles akin to the quantum mechanics that governs the universe at the most fundamental level, could simulate processes with incredible precision. These simulations could model everything from the conditions of the Big Bang to the formation of galaxies, stars, and even the hidden forces of dark matter and dark energy. These are the very mysteries that have eluded humanity's understanding for generations. The power of quantum computing could grant us a front-row seat to witness cosmic events with unmatched accuracy and reveal insights about the universe's deepest secrets. And as we look toward the future, the sheer volume of astronomical data generated by the next generation of telescopes and observatories is nothing short of astronomical. These instruments, both on Earth and in space, will collect a staggering amount of data that far exceeds the processing capabilities of classical computers. Quantum computers, however, with their unique ability to process vast amounts of data simultaneously, can analyze this information at an unprecedented scale. They can detect even the faintest signals from the cosmos, signals that our current technology might miss. From the subtle whispers of the cosmic microwave background radiation to the faint reverberations of gravitational waves, quantum computers could unlock new dimensions of understanding, revealing phenomena that may not even be visible to the naked eye. In particular, quantum computing could revolutionize our understanding of the large-scale structure of the universe. The cosmic web, a vast and intricate network of galaxies, gas, and dark matter, stretches across the observable universe. To understand how it formed and evolved over billions of years requires solving highly complex equations that take into account the interactions between gravity, dark matter, and normal matter. Quantum computers, with their unrivaled processing power, could solve these equations with greater detail and over much larger scales, shedding light on how the universe's most massive structures came to be. Moreover, these computers could help us understand the parts of the universe that lie beyond the reach of our current observational tools, offering new insights into realms that remain hidden from view. As we venture further into the cosmos, one of the most crucial challenges is ensuring the integrity of the data we collect. Quantum cryptography, another fascinating application of quantum technology, could secure the transmission of data between Earth, spacecraft, and telescopes, whether they are scattered across the globe or exploring distant regions of space. This technology would protect our valuable cosmic data from interference or corruption, safeguarding the information that will shape our understanding of the universe for generations to come. But perhaps the most profound question of all is, could there be life out there in the vastness of the universe beyond the reaches of our observable world? The traditional notion of a habitable zone where liquid water can exist might not be the only criterion for life. In fact, life may not even rely on water at all. Consider Titan, Saturn's largest moon, where lakes of liquid methane and ethane present an entirely different chemical environment. These alternative solvents could serve as the basis for biochemical processes that are completely different from life as we know it. What if life in other parts of the universe is based on entirely unknown forms of matter or energy, perhaps even tapping into dark matter or dark energy? Earth itself offers tantalizing clues through extremophiles, organisms that thrive in the harshest, most uninhabitable environments on our planet. From the depths of hydrothermal vents to the acidic hot springs, these resilient life forms challenge our understanding of what constitutes a viable habitat. If life can survive and even flourish in such extreme conditions here on Earth, who's to say it can't do the same in distant parts of the universe, where environments differ vastly from anything we experience? Exoplanet exploration, the search for planets beyond our solar system, has rapidly evolved into one of the most exciting fields in modern astronomy. Since the discovery of the first exoplanets in the 1990s, we've identified thousands of planets orbiting distant stars. With the help of advanced detection methods and missions like NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, the diversity of exoplanets is being revealed in stunning detail. From gas giants that rival Jupiter to rocky planets that may resemble Earth, the range of exoplanetary environments challenges our previous notions of what is possible. Among the most intriguing discoveries are hot Jupiters, giant planets that orbit extremely close to their parent stars, and super-Earths, planets larger than our own. These discoveries are expanding our understanding of planetary systems and fueling speculation about the potential for life beyond Earth. As we stand on the brink of these discoveries, one thing is clear: quantum computing will be pivotal in unlocking the mysteries of the universe. With its unprecedented ability to simulate, process, and analyze data on a scale never before imagined, quantum computing could propel us into a new era of cosmic discovery. The exploration of space may no longer be confined to the realms of imagination. Instead, it could become a journey of understanding, driven by the limitless potential of quantum technology. But even smaller than Neptune, and akin to rogue planets drifting through the galaxy, untethered to any star, there exists a mysterious class of celestial bodies. These distant worlds orbiting no particular sun remain elusive, yet the methods used to detect them are nothing short of brilliant in their application of physics and astronomy. One of the primary techniques used to identify exoplanets is the transit method. This approach monitors the dimming of a star's light when a planet crosses in front of it from our vantage point on Earth. The subtle changes in brightness are captured and analyzed, revealing the planet's size and orbital period. Another critical method, radial velocity, focuses on the faint wobbles in a star's motion. These wobbles are caused by the gravitational pull of an orbiting planet, and through these movements, astronomers can determine the planet's mass and composition. These ingenious techniques have expanded our catalog of exoplanets beyond what we ever imagined, giving us a deeper understanding of their sizes, masses, and even atmospheric conditions. Particularly fascinating are those exoplanets that lie within the habitable zone of their stars. This zone is the sweet spot where conditions might be favorable for liquid water to exist, a fundamental ingredient for life as we know it. Two exoplanets, Kepler 186f and TRAPPIST-1e, have ignited the imaginations of both scientists and the general public. They are viewed as prime candidates for hosting life, as their location within their star's habitable zone makes them worthy of detailed investigation. Research on these planets encompasses a variety of disciplines, from studying their atmospheres to modeling their climates, and even searching for biosignatures, chemical markers that might indicate the presence of life. The next wave of technology promises even greater insights. With groundbreaking instruments like the James Webb Space Telescope, we are on the cusp of a new era in exoplanet exploration. The JWST, with its unparalleled sensitivity to infrared light, is poised to give us detailed observations of exoplanet atmospheres. By detecting molecules like water vapor, carbon dioxide, methane, and more, we could potentially identify worlds that are not just habitable, but perhaps even inhabited. Among the most intriguing exoplanets discovered is Proxima b, which orbits Proxima Centauri, the closest star to our own sun. This Earth-sized planet, just over 4 light-years away in the constellation Centaurus, was first announced in 2016. Its discovery ignited a flurry of excitement, as it lies within the habitable zone of its parent star, meaning liquid water could theoretically exist on its surface, a crucial element for life. At 17 times Earth's mass, Proxima b is thought to be a rocky planet, similar in composition to our world. Its orbit is unusually close to its star, with a year on Proxima b lasting just over 11 Earth days. Despite this proximity, Proxima b receives only about 2/3 of the energy from its star as Earth receives from the Sun, thanks to Proxima Centauri's status as a red dwarf, a smaller, cooler star than our Sun. However, this close orbit is a double-edged sword. While the habitable zone around a red dwarf star theoretically allows liquid water to exist, it also presents significant challenges. Red dwarfs, like Proxima Centauri, are known for their powerful stellar flares, which could strip away the planet's atmosphere and expose its surface to harmful radiation. This intense activity presents a substantial hurdle for the potential habitability of Proxima b. Yet, if Proxima b possesses a strong magnetic field, it could potentially shield its atmosphere from these destructive flares. This protective mechanism might maintain conditions favorable for liquid water, making the planet an even more intriguing candidate for life. The study of Proxima b remains at the forefront of exoplanet research. Using just cutting-edge techniques, astronomers are exploring its atmosphere, surface conditions, and the likelihood of it supporting life. Observations from next-generation telescopes, such as the James Webb Space Telescope, are eagerly awaited. These instruments could reveal whether Proxima b has key atmospheric markers like water vapor, oxygen, or methane, which could be indicative of biological processes. Proxima b's discovery has sparked renewed interest in the search for life beyond our solar system. It has even led to discussions about the possibility of robotic missions, or even interstellar probes to study this nearby exoplanet more closely. Though the logistical and technological challenges of such missions are immense, the allure of discovering signs of life orbiting our nearest stellar neighbor continues to fuel both scientific curiosity and public fascination. As our observational capabilities continue to improve, Proxima b stands as a symbol of the boundless possibilities that exist in our cosmic neighborhood. It serves as a reminder of the vastness of the universe and our ongoing quest to understand our place within it. Whether Proxima b is habitable or even inhabited remains a question that we may soon be able to answer. But its discovery marks a monumental step in our journey of uncovering the mysteries of the cosmos. This breakthrough invites us to consider the vast and unknown realms beyond our current observational limits. Imagine a universe teeming with cosmic catastrophes, events so grand and powerful that they could reshape the very structure of existence itself. These occurrences, though beyond our current perception, are grounded in our understanding of physics, yet remain elusive to direct observation due to the constraints of time, space, and technology. One such event is the collision of supermassive black holes. When galaxies collide, their central black holes are destined to converge in a cosmic dance that culminates in a cataclysmic release of energy, warping the fabric of space-time itself. While gravitational waves from these cosmic mergers ripple outward, they may eventually reach us, offering a glimpse of the immense power hidden in the dark corners of the universe. The immediate vicinity of such a collision could experience profound shifts in gravitational forces, potentially disrupting entire star systems and altering the course of galactic evolution. Such events, though rare, are an awe-inspiring testament to the raw, untapped energy lurking within the universe's most mysterious objects, gamma-ray bursts. Gamma-ray Bs, the most energetic explosions known to science, are another potential catastrophe waiting to unfold. In regions rich with star formation, these bursts of gamma radiation are thought to occur when massive stars collapse or when neutron stars merge. In a matter of seconds, a single GRB can release more energy than our sun will over its entire lifespan. If a GRB were to occur in the vicinity of life-bearing planets, the consequences would be catastrophic, stripping away atmospheres, irradiating surfaces, and potentially extinguishing all forms of life. Such events are not only powerful, but also a haunting reminder of the fragility of life in the vastness of the universe. Beyond these observable events lies the concept of vacuum decay, a theoretical disaster that suggests the existence of a more stable vacuum state to which our current vacuum could transition. If triggered, this transition could propagate at the speed of light, restructuring the fundamental constants and forces of the universe as it moves through space. This catastrophic shift would render the laws of physics as we know them obsolete, fundamentally altering the very structure of reality itself. While this remains a speculative concept, its implications would be profound, changing the universe in ways we cannot yet fully comprehend. Equally speculative is the idea that dark matter, the invisible substance that makes up a significant portion of the universe's mass, could destabilize under certain conditions. If this occurs, dark matter might convert into a more stable form, releasing vast amounts of energy that could affect the gravitational scaffolding holding galaxies together. This process could ripple through the cosmos, altering the large-scale structure of the universe, shifting galaxies, and distorting the fabric of space-time in ways we cannot yet observe. These potential events are reminders of the vast, hidden forces shaping the cosmos, operating outside the reach of our current detection methods. The echoes of early universe events, such as false vacuum collapses or phase transitions, may still resonate through the cosmos, subtly influencing its large-scale structure. These phenomena, akin to cosmic inflation on a smaller scale, could create vast bubbles where the laws of physics and the density of matter fluctuate. This patchwork of galactic filaments and cosmic voids tells the story of the universe's evolution, one that is still being written in the stars. However, the vastness of the universe presents a challenge in detecting such events, particularly those occurring beyond our observable horizon. Since nothing can travel faster than light, any event beyond the reach of the light that has had time to reach us remains undetectable through traditional astronomical methods. But new theories and indirect detection methods are offering potential pathways to uncover the unknown. The study of cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang, offers one such avenue. The minute fluctuations in temperature and polarization patterns in the CMB could hold clues to events and structures beyond the observable universe. A large-scale disturbance in the fabric of space-time, for example, might leave an imprint in the CMB, potentially revealing the hidden drama unfolding far beyond our observational limits. Gravitational waves, predicted by Einstein's theory of general relativity and first detected in 2015, present another potential method for probing the cosmos. These ripples in space-time can travel largely unimpeded, offering a window into massive cosmic events. Gravitational waves generated by supermassive black hole mergers or other cataclysmic events in the distant universe might eventually reach us, providing unprecedented insight into the farthest reaches of the cosmos. Quantum entanglement, a more speculative yet fascinating phenomenon, could also offer new possibilities for detecting events beyond our observational horizon. In this quantum state, two particles become interconnected, such that changes in one particle instantaneously affect the other, no matter the distance between them. If scientists can find a way to use entangled particles to transmit information across vast cosmic distances, it may offer a method to detect events that are otherwise hidden from our view. However, the challenges of leveraging quantum entanglement for this purpose remain immense, both scientifically and technologically. Furthermore, the enigmatic forces of dark matter and dark energy could hold the key, uncovering events beyond our current observational capabilities. These mysterious components shape the expansion and evolution of the universe, and understanding their role may provide indirect evidence of cosmic events that lie just outside our ability to detect directly. In the end, while the universe beyond our observational limits remains largely a mystery, these emerging methods of detection and theoretical advances offer hope that we may one day catch a glimpse of the unfathomable events shaping the cosmos. Until then, we remain on the precipice of discovery, staring into the vast unknown, with each new breakthrough pulling us closer to understanding the true scale of the universe. And yet, numerous forces remain shrouded in mystery, potentially altering the very fate of the cosmos in ways that challenge our deepest understanding of the universe. Dark energy, for instance, is a monumental enigma, comprising approximately 68% of the universe's total energy content. It is theorized to be responsible for the accelerated expansion of the cosmos, a phenomenon that defies the expectations of conventional cosmological models. However, the true nature of dark energy and how it influences the fabric of the universe remains an area of intense speculation. If it behaves in a manner different from current assumptions, or if exotic forms of energy exist, these could dramatically alter the universe's trajectory, impacting its ultimate fate in profound ways. Similarly, dark matter, which makes up about 27% of the universe's total mass energy, holds a crucial yet elusive role. Its gravitational influence is key to the formation and evolution of galaxies and cosmic structures, yet the true substance of dark matter remains an unsolved puzzle. What if dark matter interacts with ordinary matter, or even with itself, beyond our current models? Such an interaction could lead to unforeseen consequences, throwing our understanding of cosmic evolution into chaos. As astronomers push forward with new techniques, they remain faced with the challenge of unraveling the mysteries surrounding these invisible forces. The universe's enigma doesn't end there. Beyond the known forces of gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, there may lie undiscovered fundamental forces or interactions that we have yet to comprehend. Theoretical physics suggests the possibility of a fifth force, or modifications to existing forces, especially at extreme cosmic scales. These unknown forces could provide a key to understanding anomalies in cosmic behavior, altering everything we know about the universe's evolution. Additionally, quantum mechanical effects on cosmological scales, such as those associated with quantum gravity, could unleash phenomena that dramatically reshape the cosmos. Quantum fluctuations during the early universe may have left imprints on the cosmic structures we observe today, influencing their development across time. Moreover, the notion of extra dimensions, dimensions beyond the familiar three spatial ones and one temporal dimension, opens up an exciting new frontier in cosmological speculation. Could these dimensions exist and exert observable effects on cosmic scales? If they do, they could introduce a completely new set of dynamics that would rewrite our understanding of the universe's fate. In this vast and ever-evolving cosmos, one thing is certain: the deeper we probe, the more questions emerge. The universe is also home to phenomena that defy explanation, like fast radio bursts, FRBs, brief, intense bursts of radio waves originating from distant galaxies. While their exact source remains uncertain, the high energy and transient nature of these bursts suggests the involvement of exotic astrophysical phenomena, or perhaps interactions with previously unknown cosmic entities. Similarly, the discrepancy between the observed distribution of matter and predictions based on current gravitational models adds another layer of complexity to the cosmic puzzle. This missing mass problem, sometimes called the dark matter problem, suggests the existence of unseen matter that eludes detection by conventional means. These anomalies are reminders that our models of the universe are still incomplete, and new physics may be required to solve them. Beyond this, the cosmic microwave background, CMB radiation, has presented further unexpected anomalies, particularly in its polarization rather than its temperature. These peculiar alignments in polarization suggest unexplored aspects of cosmic inflation and may hint at physics yet to be discovered. As astronomers analyze the CMB with ever-increasing precision, the potential for breakthrough discoveries continues to rise. The motions of distant galaxies, sometimes defying the predictions of standard cosmological models, also raise red flags. Some galaxies appear to be speeding in ways that do not align with our understanding of cosmic dynamics, potentially indicating unseen forces at play, or gaps in our comprehension of the universe's large-scale structure. One of the most fascinating anomalies of all is the Great Attractor, a mysterious gravitational anomaly located in the direction of the Hydra and Centaurus constellations. The Great Attractor exerts a powerful pull on galaxies within its reach, including our very own Milky Way. What makes it particularly intriguing is its effect on the motion of galaxies, suggesting the presence of an immense, unseen mass. Yet, despite its gravitational power, the Great Attractor remains largely elusive, with its true nature and composition still unknown. As we continue to explore the universe, new phenomena and mysteries emerge regularly, challenging our most established theories and prompting us to reconsider the fundamental forces at work in the cosmos. From the discovery of strange radio bursts to the enigmatic behavior of dark matter, every new anomaly only deepens the mystery of the universe's ultimate fate. With each breakthrough, we inch closer to a deeper understanding, but the final answers may be far more complex than we ever imagined. But as we peer deeper into the cosmos, an astonishing mystery arises: the discovery that there are regions of space seemingly defying the expectations of universal expansion. In fact, galaxies are being drawn toward a particular point in space at an unexpectedly high velocity, challenging what we know about the expanding universe. This area, often referred to as the Great Attractor, exerts a gravitational pull so powerful that galaxies within its reach are accelerating faster than what would be predicted by the known rate of cosmic expansion. While it has intrigued scientists for decades, the true nature and composition of the Great Attractor remain obscured. Hidden behind dense star fields and the ever-present clouds of dust in the Milky Way, its enigmatic force continues to fuel theories, including the presence of a massive dark matter concentration or the influence of unseen superclusters of galaxies, concealed from our view by the vast stretches of intergalactic space. This cosmic anomaly sparks a deeper curiosity about the nature of the universe itself. As we attempt to comprehend such perplexing phenomena, the concept of interstellar travel beckons, a dream of reaching distant stars, exploring galaxies beyond our own, and perhaps even venturing beyond the boundaries of the observable universe. While our current understanding of physics presents enormous challenges, the idea of journeying between stars remains tantalizing. The distances between stars are mind-bogglingly vast, and even the nearest neighbor to our solar system lies many light-years away. Yet, in the realm of theoretical physics, exciting possibilities are emerging. Hypothetical technologies, such as nuclear fusion-powered spacecraft or antimatter engines, could potentially allow us to travel at a significant fraction of the speed of light, enabling interstellar journeys that were once confined to the realm of science fiction. Interstellar travel is not merely about crossing vast distances. It offers the opportunity to study far-off celestial bodies firsthand. By reaching distant star systems, humanity could study exoplanets, examine the potential for life beyond Earth, and observe cosmic phenomena up close, phenomena such as black holes, neutron stars, and other exotic astrophysical objects that lie beyond the grasp of our current telescopes. This quest to explore the unknown could unlock fundamental insights into the very fabric of the universe. And as our imagination stretches beyond the reaches of current technology, ideas like warp drives and faster-than-light FTL travel are being discussed, opening doors to the unimaginable. These ideas challenge our current understanding of space, time, and energy, yet they hold the potential to revolutionize our journey through the cosmos. One such theory, the Alcubierre drive proposed by physicist Miguel Alcubierre in 1994, envisions a spacecraft traveling faster than light by warping the fabric of space-time itself. Imagine a warp bubble around a spacecraft, where space-time in front of the ship contracts while it expands behind it. The ship remains stationary inside this bubble, yet it effectively moves faster than light relative to the surrounding space. While this concept presents an intriguing solution, it relies on the manipulation of exotic forms of energy, such as negative energy or negative mass, that have never been observed in nature. Moreover, the enormous energy required to create and sustain a warp bubble remains a daunting challenge. Similarly, wormholes, hypothetical tunnels through space-time, offer another theoretical means for faster-than-light travel. If such tunnels existed, they could connect distant regions of the universe, allowing a spacecraft to bypass the limits of light speed travel. However, like the warp drive, the idea of traversing wormholes comes with its own set of challenges. For instance, the stability of a wormhole remains uncertain, and it would require exotic matter to keep it open. Even if wormholes could be stabilized, we would still face significant hazards in navigating them, making their practical application for interstellar travel a speculative dream. At least for now. But what would happen if we could somehow overcome the cosmic speed limit and venture beyond the observable universe? Currently, the observable universe represents the portion of space from which light has had sufficient time to reach us, about 13. 8 billion years since the Big Bang. Beyond this boundary lies a vast expanse of the cosmos that is beyond our reach due to the finite speed of light and the expansion of space itself. Still, some theorists speculate that the universe beyond the observable horizon may resemble what we already see, a patchwork of galaxies, stars, and other cosmic structures, but with unique characteristics and perhaps even new forms of matter. Others propose more radical ideas, such as the existence of parallel universes or alternate dimensions, each governed by different laws of physics. These ideas, if true, could radically expand our understanding of existence itself. Could we one day traverse the universe, stepping beyond the edge of what is observable and into realms governed by unfamiliar laws of nature? While these questions remain speculative, they continue to push the boundaries of scientific inquiry, urging us to explore the farthest reaches of space and the deepest mysteries of reality. The allure of interstellar travel and the potential to witness phenomena that have yet to be seen by human eyes ignites the imagination, offering a glimpse into a future where the exploration of the cosmos may one day be within our grasp. Our observations, when examined through the lens of cosmic evolution, will inevitably be subject to the profound effects of time on a scale far beyond human comprehension. Over vast stretches of time, we may bear witness to the aftermath of cosmic events and phenomena that occurred billions of years ago. These ancient relics hold the potential to offer extraordinary insights into the history and evolution of the universe on a grand, sweeping scale. But it is not just the observable cosmos that beckons our curiosity. The vast realms beyond our current observational reach challenge our understanding in profound ways, carrying significant philosophical weight. What exists in these uncharted territories? And what does that tell us about the very nature of existence itself? Indeed, venturing into the unknown beyond the observable universe carries with it one of the most profound philosophical questions humanity has ever faced. What is our place within this vast, ever-expanding cosmos? The scale of the universe, both observable and potentially unobservable, provokes deep reflection on humanity's significance in the grand scheme of things. Are we merely a fleeting speck in the infinite expanse of space, or do we have a more profound purpose in the greater story of existence? The concept of an unobservable universe directly confronts us with the limitations of our human understanding, highlighting the constraints of our scientific methodologies and empirical observations. There may well be aspects of the universe forever hidden from us that we may never comprehend. This realization shakes the foundation of what we believe is possible, and it's forcing us to grapple with the boundaries of human knowledge. Moreover, the possibility of multiple universes, suggested by the bold theories surrounding the multiverse, opens up new realms of thought. If our universe is but one of many, each with potentially different laws of physics and constants, what does this mean for the very fabric of reality? Are we unique, or do parallel realities exist with their own histories, trajectories, and forms of life? This inquiry leads us to the core of existence itself, prompting questions about the origin of the universe, the nature of time, and the possibility of life beyond our own cosmic neighborhood. As these questions unfold, scientists worldwide are tirelessly working to push the boundaries of human exploration. Their mission: to uncover what lies beyond the observable limits of our universe. Particle accelerators, such as the Large Hadron Collider (LHC), are pivotal in this quest. These machines replicate conditions that existed just moments after the Big Bang, unlocking the potential to discover new particles or forces that could fundamentally alter our understanding of the cosmos. Gravitational wave detectors like LIGO and Virgo have already made groundbreaking strides by detecting ripples in space-time from distant cataclysmic events. These waves, originating from cosmic occurrences such as merging black holes, carry crucial information about the most extreme environments in the universe. As sensitivity improves, we may even detect gravitational waves originating from realms beyond our observable universe. Space observatories, such as the Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope, scan the cosmos for high-energy phenomena. By studying these events, scientists hope to uncover clues about the behavior of matter and energy under the most extreme conditions, potentially shedding light on regions that remain hidden from view. In the search for dark matter, experiments like those investigating the elusive WIMP particles hold the promise of revealing unseen structures and forces that shape the universe. Telescopes such as the James Webb Space Telescope, JWST, and the upcoming Large Synoptic Survey Telescope, LSST, are poised to redefine our understanding of the universe. By capturing detailed images of distant galaxies, mapping the distribution of cosmic matter, and studying the cosmic microwave background radiation, these instruments will provide unprecedented insights into the nature of the cosmos, stretching our vision far beyond the limits of what is currently observable. As we conclude this journey through the farthest reaches of the observable universe, we are left with a profound sense of awe. The scale, complexity, and beauty of the cosmos, with all its mysteries, is staggering. Our exploration has taken us to the edge of the known universe, offering tantalizing glimpses of what lies beyond. Thanks to the tireless efforts of scientists, engineers, and explorers, we have unraveled mysteries that once seemed unimaginable. From the strange nature of dark matter and dark energy to the mind-bending possibilities of wormholes and multiverses, each discovery has brought us closer to understanding the fabric of reality itself. However, even as we uncover new layers of knowledge, we are constantly reminded of the limits of our understanding. With every new discovery, countless questions arise, questions that challenge us to push the boundaries of what we know even further. What do you believe lies beyond the observable universe? Is there a vast emptiness that stretches forever? Or could there be something so incomprehensible that we can barely begin to grasp it? Leave your thoughts in the comments below and subscribe to our channel Starflux for more documentaries like this. Thanks for watching.